And this is X4, questions 14 and 15. So they are simultaneous move games, and in particular, they are about how to solve mixed strategy Nash equilibria. So there are two ways of doing this. The first one is just use the indifference condition, and that's kind of a trick, but for small games like this, it should work. So I'm going to do it for question 14, and for 15, I'll like draw the complete best response function. So that's kind of a safer way to solve these. So I will show you both ways. So if you want to use the best response function to solve question 14, you can do that as well. So, but I'm not going to do it. I'm going to try to solve it quickly. So what I mean by indifference condition is we just assign probabilities, say p and 1 minus p, and q and 1 minus q. And what I'm going to say is for the role player, I need to be indifferent between b and s such that the other player will mix. Let me say that again, that's wrong. So I'm going to pick the probabilities such that the other player is indifferent between the actions B and S. So let's do it for the role player first. So for the role player, in order for me to be indifferent, let's say, if I play B, I will get 6 and 0. So again, the condition I want is this. So if I play B, I will get 6 with probability Q, and I will get 0 with probability 1 minus Q. And if I play S, I will get 0 with probability Q plus here 3 with probability 1 minus Q. So in order for me or for the role player to mix, the column player must mix in a specific way, which is set Q equals to the solution of this expression, which is, I think, 3 over 9. Let's see. 3 over 9, yeah. So it's 1 over 3. Again, in order for the role player to mix, the other player needs to mix in a way that's 2/3, 1/3. 1/3, 2/3. So we can do exactly the same thing for the other player. So we want B, the expected value from B is the same as the expected value from S for the other player. When I say other player, it's the column player, sorry. So if I play B, I will get either 3 or 0. 3 with probability P plus 0 with probability 1 minus P. And I want to set that equal to here 0 with probability P plus 6 with probability 1 minus P. So again, if that happens, if I mix this way, then the other player will be indifferent between B and S, so the other player will mix as well. So that's basically the indifference condition. So we can get 6 over what number? 9 again, so it's 2 over 3. So in general, if these numbers are the same, then the P's and Q's are going to be symmetric. But if these numbers are not like 3 and 6 and 6 and 3 like that, then you need to solve for 2 different probabilities. But here I'm doing P is 2/3, so B with probability 2/3 and S with probability 1/3. Oh, and the question is just asking for the expected payoff, so we don't even need to compute that. We can just substitute this thing back into our expression. So if we are asking for the column player's expected value, then we can just substitute in this thing back in here. So it's basically 3 times P, which is 2 over 3, or we can check it, 6 times 1 over 3. In both cases, it's equal to 2. So for the role player, the expected payoff is 2. We can compute it for the for the column player, the expected value is 2. For the role player, we can substitute this a third into here, which is, well, since again the game is kind of symmetric, so it's also 2. If you do 6 times a third or 3 times 2/3, you'll also get 2. Okay, so that's the indifference condition way. And for question 15, I'm going to just draw the best response functions. It is already drawn here, but I'm going to draw the whole thing, just redraw the whole thing. So in order to figure out the best response, I need to first, let's say, figure out the role player's best response. There are 3 possibilities. One is best response is U, one is D, and the other one is I don't care. So U or D or any kind of mix. So in order for me to prefer U, my expected value from U should be larger. So let's call this Q and 1 minus Q again, and this P and 1 minus P again. If I prefer U, it means I get 5 or 0 from U, which means it's 5Q. It should be larger than I get 0 or 10 from D, which means it's 10, 1 minus Q. And when they are equal, then I don't care. When they are equal, then I get the same from U or D, so I can do whatever I want. So in particular, I can just mix with any probability. I can just do the random thing. If I prefer one of them, I'm not going to do the random thing, right? I can just do that for sure. If I'm okay with both, then I can actually do the random thing. So that's only when these two are equal to each other. And by the way, that's just the indifference condition from the previous question. And at the end, when we have D, then it's just flip that. Let's see, I'll just flip it. And we should probably solve this. This is Q is larger than or equal to 2 over 3. I think that's the case. It's 10 over 15. Yeah. All right. Let's see if the diagram is drawn correctly. So we have Q is the probability that we are playing left or right. So Q is this value here. And if Q is larger than or equal to 2/3, so 2/3 is the probability we are playing L. So here, this is Q is 1, this is Q is 0. So this point is indeed Q is 2/3. So one thing to be careful about is when you draw the diagram, on the left it's actually Q is 1, on the right is Q is 0. So if you want to flip this and draw it the other way, that actually may be a better choice. But in any case, since I drew it this way, then I'll just say this is 2/3 and this is 1/3. And when Q is larger than 2/3, so if in this region, the best response is going to be U. So here, note that this is a U. Let me use this color. So this is U, so I'm going to best respond by playing U. So that diagram is actually right. And when Q is less than 2/3, then we're in this region, then the best response is D. So again, the diagram is right. So that's good. And when they're equal, then I don't really care. I can just do either just U or either I can do D, and anything in between is okay for me. So that's, suppose I'm the role player. And next, suppose I'm the column player. Best response of the column player, we can do exactly the same thing. Let's see what will happen. When would I play left? And when would I play right? And when would I mix? So I play left if I get what I get from left, which is these two. 9 is larger than or equal to what I get from right, which is either 9 or 0, 9 was probably P. Okay, so it means if P is smaller or equal to 1, well, that's like everything. If P is smaller than or equal to 1, I'm going to just pick left. And mix, if P is equal to 1, I don't care, because they are equal. So let me actually write the original form. 9 is equal to 9 times P. And on the right, I will pick right if 9 is smaller or equal to 9P, which means P is larger than or equal to 1. But P is a probability, so P is 1. So both of these two cases is P is 1. And let's actually draw this. If P is, what is P? So P is the probability of playing U. So this is P is 1, then this is P is 0. So again, the diagram is kind of flipped on the horizontal axis. I don't know why. But in any case, if P is less than or equal to 1, basically P is anything, I'm going to best respond by playing L. So we have L here, so that's actually correct. That's my best response. And if P is 1, then I can mix, I don't care. So that is this region, P is 1 region. Okay, so now we have the diagram. And what's the definition of Nash? Nash is when we have mutual best responses, and these are the best response functions. So of course, we can just highlight the region where we have best responses. So this is a region of Nash. And let's do a sanity check. Let's highlight the pure strategy Nash and make sure that it is actually this point. This point is UL, right? So let's check. So let me get rid of everything. So if the other player is playing, if the column player is playing L, I prefer U. If the column player is playing R, I prefer D. If the row player is playing U, I prefer both. If the row player is playing D, I prefer this. So now I highlighted the pure best responses, and this is the only Nash. And as we found out, it's U and L, which is this point here. So we're good. And we have one pure strategy and an infinite number of mixed strategy Nash. And what is the question? So the question is asking the smallest and largest probability of mixing. So the smallest and largest we have just in this region, right? So the smallest is 2/3 and the largest is 1. So for this question, there are actually many different versions. So sometimes it's between 0 and 2/3, and sometimes I'm asking for the other player. So the best way is actually you should be able to draw the diagram. So you should be able to write down the best response function, and you should be able to draw the complete thing, and then you will figure out in which region we have mixed strategy Nash. So in this case, if you only solve this indifference condition, you will get the number, but you don't know whether it's on the left side or on the right side. So it's actually important that you write down the whole best response function, and then figure out in which region we have best responses. So don't just figure out this number, because you don't know whether it's on the left or on the right.